Hello, everyone, to the Friday morning lecture. Today, we are lucky to have Max Piskunov speak to us about SetReplace local multiway systems and related tools. Those of you who know Max, I do not need to say much, but for some of you, let me introduce a little bit about our esteemed speaker. Max originally did his PhD in, he studied theoretical physics, and he was at Northeastern University in Boston working on cosmology, on theoretical models of cosmology. And later on, Max joined Stephen Wolfram's team, and that's a while back. And Max is one of the early people who, with Stephen, started the Wolfram physics project. So much of what you are doing now and some of the things is due to his initial work. In fact, the set replace tools that Max is going to present was the original backbone of the Wolfram physics project and still serves as much of the technology for what many of you are using. So it's really nice to have Max speak to us and give us an inside view on these things, and also some of the local multiway systems that he has been developing. Besides physics, Max is very passionate about software engineering, and over the years, he's been one of the top programmers in various capacities. So it's great to have you, Max. Thanks for being here, and go ahead, give the stage is all yours.
Thanks. So, hello everyone. Let me share my screen. Okay, so I'm going to tell you about set replace and non-determinism, and specifically is a local way of thinking about non-determinism, which I call local multiway systems. And so set replace is a package for evaluating multi-set and hypergraph substitution systems, and it's the code that basically was used at the beginning of the Wolfram physics project. And in particular, it has an efficient algorithm in C, written in C++ for running hypergraph substitution systems. And so there's going to be 4 parts to my talk today. So first, I'm going to explain what multi-set and hypergraph substitution systems are on a very basic level from the first principles. Then I'm going to talk about non-determinism and local multiway system. Then I'm going to explain what the current state of set replace is after about 3 years since I was last working on it. And finally, I'm going to talk about the problem of expression deduplication. And if we have enough time, about some open questions that I have related to that. So first of all, what is a multi-set substitution system? So the state of the multi-set substitution system is an unordered multi-set of expressions. So for example, here the expressions are just numbers, and so order doesn't matter. And then the rule takes a subset, which is just can be a subset of any patterns, and then it replaces it with another subset. So in this example, we take any 2 expressions A and B, and then we replace them with the sum A plus B, A minus B, and then A times B. And so, for example, we can match 8 and 5. And 8 and 5 is just an example. Of course, you can match any of the 10 pairs of numbers here, and that is related to non-determinism that I'm going to talk about later. But as an example, let's say we match 8 and 5, and then we can apply the rule and get 13, which is sum 3 and 40. And we can then keep applying the rule and get the evaluation of the system. So now let's see a different way of looking at the evolution of the system, which is an expression events graph. And so for that, the expression events graph is on the right. And in the beginning, we just have the initial state, which is represented by 5 expressions. And then, so expression events graph has 2 types of vertices. It has an expression vertices and event vertices. So when we have an event that takes 8 and 5 and takes 13, 3, and 40, we add a corresponding event to the expression events graph. And then we keep adding events, event vertices. And so at the end, we can see the entire evolution of the system in this expression events graph. And so to talk about some terminology, so each event destroys some expressions and then it creates other expressions. So for example, event 1 here destroys 8 and 5 and creates 13, 3, and 40, and so on. And then to figure out what the final state is, we just need to find all of the expressions with the out degree of 0. And so in this case, you can see them highlighted. And in a single way evolution, the rules can only take as an input the expressions with which are leaves. So the out degree needs to be 0. Okay, so let's talk about the hypergraph substitution system now, also known as the Wolfram model. So the hypergraph substitution system is a special case of the multi-set substitution system. And so in this case, the state is also an ordered set, but expressions are ordered lists of atoms. And so in this case, we have 3 expressions which all have arity of 3. And so these expressions in the case of hypergraph substitution system correspond to hyperedges. And the atoms, and by the way, the word atom here has nothing to do with atoms from physics. It just means they're atomic, so they don't have any internal structure. And so the atoms are just labels, they can be numbers or letters or anything. And the only thing important about them is that some of them can be shared between different expressions. So in this case, there is 2 that's shared and 4 that's shared. And so we can visualize it by plotting each of those hyperedges as a polygon. So for example, we can plot 1 to 3 as 2 edges, 1, 2, and 2, 3, and then we can fill the entire thing as a triangle. And then similarly, we can plot 2, 4, and 5 as well. And here you can see that 2 is shared. And the same for 4, 6, and 7. And so this is an ordered hypergraph. Ordered means that each hyperedge expression is an ordered list. And hyper means that hyperedges can have any number of atoms, not just 2. So in this case, the hyperedges are arity 3. Okay, so now let's talk about what the rules are for the hypergraph substitution system. So because it's a special case of the multi-set substitution system, the rules can still be written as patterns, but they are a special case, so there are restrictions on these patterns. So in particular, on the left-hand side, we can only have simple patterns that don't try to examine the internal structure of atoms. And the only non-trivial thing about this left-hand side pattern is that some of the patterns can be the same. So for example, here, the pattern A is the same, which means the first atom in the first input hyperedge should be the same as the second atom in the second one. And so, for example, the A can match to 2, and the patterns can match like this. And then they replaced with the right-hand side. And again, the right-hand side can just be rearrangement of atoms on the left. And so if you now take this initial state again and apply the rule to it, you can see that it changes over time. And here we get the final state. So one other thing we can do in the hypergraph substitution system is we can create new atoms, or equivalently create new vertices. And so the way it looks in the pattern rules is that we can put the module on the right-hand side and then create a new variable in the module. And so if you've written functions in Wolfram language, you would know that module has two arguments. Now, in the first argument, you have a list of variables that it would create, and then you can use this variable in the second argument. And so in this case, we create a new variable f, and then we use it in the hyperedges in the output of the rule. And so module just creates a new variable, which is a new atom. And so if you run it now, then it will grow the hypergraph. And so for the Wolfram model of hypergraph substitution systems, there is a shorthand notation we can use instead of this pattern rule, because the patterns always have the same form. So the left-hand side are always single patterns. So we can just drop the patterns. And on the right-hand side, we can drop the module because we know if a symbol appears on the right, it doesn't appear on the left, then it's a new variable. And once we do that, we can also replace the variables with just numbers. And so we get a form for hypergraph substitution rules that you might be familiar with from Wolfram physics project materials. And so the left-hand side is still patterns, and the right-hand side has an implicit module. But this form of rules are, they're shorter and they're easier to enumerate and so on. Okay, so let me give you a demo of how all of it works in SetReplace. Okay, so first of all, you can find SetReplace if you go to setreplace.org. And it's a repository on GitHub. And in particular, there is a lot of documentation. So if you want to see how to use any particular function, there's a full list of functions and properties here. So you can take a look. So then the repository has instructions of how to build it, but as of right now, the build system doesn't actually work, but you can still install it from the package server. So you can just do package install of SetReplace, and then you get the latest version. And then you just import it, and then you can use it. And so one of the main functions in SetReplace is Wolfram model. And if you used a resource function Wolfram model, it's actually the same function. So what resource function does is that it would download and install SetReplace and then call the Wolfram model from SetReplace. But you can also just use it directly. And then again, there's a documentation page listing all of the different options. And so by default, the rules in Wolfram model would be the short notation of the hypergraph substitution system rules. But you can use pattern rules as well, the full multi-set rules. And so to do that, you just put an association with a single key for pattern rules. And then you use your pattern rules as a value. And then the second argument is the initial state. And the third argument is the step count specification. And so one way to specify the step count is to specify the maximum number of events you want to run the system for. So for example, here you'll run it for 8 events, and you will get this Wolfram model evolution object. So Wolfram model evolution object is just internally an association that has different information about evolution. And so you can see it says a trend for 2 to 3 generations, and I'm going to explain later what generations are. But it also says that you have 8 events, and then it terminated because it reached max events. But there could be other termination reason. For instance, if it just ran out of rule matches, it could be a termination reason as well. But in this case, it reached 8 events. And then internally, you can just look at part 1 of this Wolfram evolution object, and you see all of its contents. And so in particular, it has all of the expressions here. So it says atom list, but actually these are just expressions. And then the event input and outputs and so on. And so the way you use Wolfram evolution object is that you get different properties of it. And so, for example, you can get all expressions, which are just all expressions that appear throughout the evolution. And then you can, there's the properties that will tell you everything you can do with it. So another example of property is all event states list, and that will show you a list of state between every event. So this is the initial state, and then you can see it took 2 and 8, kept 2, 5, and 2, and then replaced 2 and 8 with 10, -6, and 16, and so on. You can also get a final state, which is the same as the state here. And you can also get a state after a particular number of events. So there's a state after 2 events. And you can also count from the end by putting negative numbers. So this is a state, -3, 3 events from the back. So one of the properties of expression events graph. So you can get it for this system. And then expression event graph is just a graph object, and you can pass different options to it as well. So for example, you can have the vertex labels go to name, and that just shows the internal vertex labels. And in this case, they're just events and expressions that are indexed because the contents of expressions can be the same. And the vertex name just have indices. But if you put vertex labels goes to automatic, then it would label the expression vertices with actual contents of those expressions. And so then you can actually see what the system is doing fairly clearly. Okay, so now I can explain what the generations are. So here in the expression events graph output, the layers at which it puts different vertices are not arbitrary. So in fact, every layer corresponds to a generation. And first of all, every layer can only have either expressions or events. You would never have an event and expression in the same layer. And then it would always put expression or event as high, vertically as possible. And then the layer at which a particular vertex is corresponds to a generation. And so in other words, a generation of the event is a maximum of generations of its inputs plus one. So for example, generation of the initial state is 0, and then generation of this event would be 1, because all of its inputs have generation 0. And then generation of this layer is 1, but then generation of this event is 2, because even though one of its inputs has generation 0, another input has generation 1. And so its outputs are generation 2. And so on. And so the intuitive way to think about generations is that to go from one generation to the next, you just evaluate everywhere in the state once. And so there's a shorthand notation shorthand syntax to accept generations, and you can just use it like this. So if you call the Wolfram evolution object at 0, you get the initial state. Then 1, you get the third generation. 2, you get the second generation. -1, you get the last generation. And so note here it says generation 2 to 3. So what it means is that it got some expressions from generation 3, but it didn't get all of them. And so there are still some expressions that can be matched to get more expressions in the third generation. So for example, you can see here, it can match 410 -21 and -96. So 2 events of the third generation are missing. And that's why it shows 2 to 3 rather than just 3. But you can also run Wolfram model for specifically 3 generations. And then you can see you get 2 more events, and you get full 3 generations, and now just at generation 3. And actually running for fixed number of generations is the default. So if you just put 3 here, you will get the same thing. And then you can also use different graph layout if you want. So of course that would not show you any generation information, but it might be useful if you expect the expression event graph to have some topological, some structure, for example, like it might be like in some cases, expression event graph is a grid, but it might be easier to see in a spin electrical embedding. So you can do that. Okay, so let's then get to hypergraphs. There is a hypergraph plot function that shows ordered hypergraphs. So for example, we can plot the 3 hyper edges, 3 of arity 3 and 1 of arity 4. And so the output of hypergraph plot are not graph objects because they have extra structure to them, but they use graph internally and they have a lot of options that are similar to graph options. So in particular, you can do vertex labels. Then if you have hyperradius authority 2, then it just looks like an ordinary graph. You can also have hyperradius authority 1, which is a hyperradius contains one vertex, in which case it would put a circle around it. And then if you have multiple of such hyperradius, you get multiple circles. And then you can have self-loops. You can also have RET3 double self-loop, in which case, similar to hyperradius here, it will put a polygon around the whole thing, so that's how you can distinguish them. And similar, triple self-loop of RET4. And then you can have more complicated cases too, with the hyperedge 1, 2, 2, and 1, 2 to 1. And I mean, if you have a small number of vertices and a lot of hyperedges with large arities, at some point it will get hard to understand what's going on. But then you can always just use text representation. Okay, so let's talk about rules now. So there's a function called rule plot, which will just give you the rule. And so here it would put vertices in the same places on the left and right hand side. So you can see what's going on. And then if you run for 10 events, we get this final state. And so there's one property. So in the presentation, I was showing some evolution videos. So there is no property to generate evolution videos. There is some code on GitHub in one of the open issues you can check, but it never got merged to SetReplace. But there is an event state plot list property, which kind of allows you to see what the evolution is doing. And so here it shows you states after every event. And then it shows in gray the expressions or hyperedges that are going to be destroyed by the next events. And then it shows in red the hyperedges that just been created. And then if the hyperedge just created and then going to be destroyed, it's going to be red and dashed. And so you can see here what the evolution is doing. And then you can get an expression events graph as well. And also a causal graph. And causal graph is it's just a kind of a short form of expression events graph. And in case of single way evolution, it doesn't actually lose any information because it just replaces every token with an edge. But yeah, in the multi-way evolution, expression events graphs more useful, but we'll get to that later. And then we can also have a rule that creates an atom, in this case 6. And you can see it in the rule because the atom 6 will have a different color and then there's not going to be a vertex corresponding on the left. And then you can run that for 60 events. Get the final state of that. And again, because the core of SetReplace in C++, it's actually pretty fast. So you can run for 10,000 events in under a second and get the final state plot of that. So that's the expression events graph. And that's the event states plot list. Okay, and then there's also a helper function to pattern rules. And so if you want to see what a shortcut notation for a Wolfram model rule looks actually does, you can do pattern rules, and then you can see the full version. And so keep in mind that the way Wolfram model works is that it would always convert the short form rule into the pattern rule. And then it actually has some logic to figure out if it can run the pattern rules in C++ or not afterwards. And so actually, if you just like the form of pattern rules, you can use them without any performance penalty, as long as they are simple enough and they don't have any conditions on the left-hand side and so on. It will just work. Okay. So let's get back to the talk. And so now let's talk about non-determinism. So in some systems, well, actually in almost all hyper-substitution systems, there are multiple places where you can apply the rule. So for example, here, the rule takes one hyperedge as an input and produces 3 hyperedges. But we have 2 hyperedges in the state. And so you can match either expression 1, which is a self loop, or 1, 2. So if it matches 1, 1, you get one state. And if it matches 1, 2, you get a different state. But in this case, it actually doesn't matter in which way you apply this rule. Because you can see after one event, you get different states. But then if you apply the other event, you get the same states. And you can see that very clearly in the expression events graph, because it just disconnected. And so the expression events graph doesn't even have the information in which order you apply the events, because you either build the left side of it first and the right side of it first, but the end result is always the same. But that's not always the case. So for example, here, in the input of the rule, we take a pair of adjacent edges, and there are 4 possibilities that we can do that. And of course, once we use one of the pairs, then we cannot use the same edge again, because the rule now destroyed it. And so here, if we use different evaluation orders, you will get different states. So here you can see 2 examples with different event ordering functions. And you can see they're different because there are 2 high-degree versions on the left, and they're in different places on the right. And so they have different expression events graphs as well. And in particular, the expression events graph for the first event ordering function has 2 disconnected components, whereas the second one is weakly connected. But what you can also do is that you can combine both of them into a single expression events graph. And so this is now a local multiway system expression events graph. And you can see it's a real multiway system because there are expression vertices without degree that's larger than 1. And so that means the same expression can be destroyed by multiple events. And that means there's some non-determinism. But the single-way expression event graph are just subgraphs of this graph. So for instance, the highlighted one now is the first one that has two disconnected components, and this is the second one. And to be able to actually generate the evolution of the entire multiway system, it's important to understand which of the expressions can be matched and which of the expressions can be in the input of a single event. And so to understand how to do that, we need to understand the expression separation. So there, like a pair of events in physics, there are three kinds of separations you can have between events. So you can have time-like, but between expressions. So you can have time-like pair of expressions, space-like, and also branch-like. So time-like means that there is a path that exists from one to another. So for instance, for this pair of expressions, 1, 2, and 2, 5, they are time-like because they're causally related. There is a path in the expression event graph from one to the other one. Then this pair, 2, 5, and 8, 3, are space-like separated. And the way to see that is that all of their last common ancestors are events. So this is actually a slightly non-trivial statement. So fundamentally, what it means for two expressions to be space-like is that they can appear together in the same state during single-way evolution. But what that means more specifically is that if you take a union of incomponents of those two expressions, that union, so all of the expression vertices in that union will have the out degree of at most one. But you can show, I mean, if you want a proof of that, you can ask me, but that's actually equivalent to all last common ancestors of the two pair of the pair of expressions to be events rather than expressions. And I mean, intuitively, you can see that because for expressions to be compatible, you want them to be produced by events rather than be branching from expressions. And so this is another example of a pair of expressions which are branch-like. And you can see the branch-like because they branch out from another expression. And in this case, it's obvious they cannot appear in the same state because for them to appear in the same state, the two events, they depend on must coexist. But those two events consume the same expression as an input, which makes them incompatible with one another. And so this is also how you can run the entire multi-way system more efficiently than you would do with global multi-way systems. When you just have entire states, and then for each step of the evolution, you apply a rule somewhere in the state, and then you copy that state, and you just repeat that. And so, in fact, you can have a data structure that's quadratic in the number of expressions. And then you can have an algorithm that would run the multi-way, the local multi-way system in quadratic time. And so that's implemented in the SetReplace. And then if you run it for the entire system, you get the whole space-like multi-way system. Yeah, and so one other thing I can mention is that you can reconstruct states from the expression events graph here in the following way. So you can start by picking some expression without degree 0. So that would be one of the leaf expressions. And then you can keep adding more expressions which are space-like with all of the expressions you already have. And then to get a state that would actually appear in some single wave evolution that's part of multi-wave evolution, you just need to get a maximal state, a maximal set of such pairwise space-like expressions. And then the enumeration of all such maximal sets is going to be all possible states. And of course, in general, you might have an exponential number of them, but that's how you can reconstruct them. Okay, so let's do a second demo. And so there are two options that are relevant here. So there's an event ordering function and the event selection function. So the event ordering function it specifies in which order to run the evolution. And so you can read the documentation here, but the way you specify it is by list of different criteria, which are going to be, the precedence from first to last. Yeah, but for this rule, if we use the default event ordering function, you get the case with a disconnected expression events graph. And then if you use the event ordering function called new stage, which means it will try to pick the edges that have just been created instead of the oldest one, which is the default. Then you kind of get depth first evolution. And so you get a completely different state. And the expression event graph just looks like a line because it keeps reusing the same expressions. As an event selection function, by default, it would run a single way evolution, meaning that it would never use expressions that have already been destroyed. But you can also specify it to be multi-way space-like, in which case it would run the multi-way system. And then you can get the expression events graph for that. And so, for example, in this case, it produced the entire multi-way space-like system for 2 generations. And so you have expressions, so all possible expressions that can be produced during any single way evolution would be in this expression events graph somewhere. Okay, so in other words, what this allows us to do is that in the single way evolution expression events graph, all of the expressions have the out degree of 1 and in degree of 1. Here, we are able to have expressions that have still in degree of 1, but out degree can be greater than 1. Okay, and there is later I'm also going to talk about the problem of how to also make in degrees larger than 1, which is a problem of expression deduplication. But before we get to that, let me explain what the current state of SetReplace is. And so SetReplace has 11 contributors in total, but the commit interval is from end of 2018 to September of 2021. And unfortunately, I haven't done anything with it since then. And so if you run it on the latest Wolfram language, some things are not working. So in particular, if you run all the tests, 40 tests fail, which is not good. But for the for full transparency, let me just explain everything that's not working. So there's a SetReplace git SHA constant that's not working, and that's because there's a git link package that is used to interact with Git, and that doesn't seem to be working anymore. So then 29 tests fail because there are issues with the tests themselves, so they don't affect any of the functionality. You just cannot run the tests. Then there are 9 failures related to the experimental implementation of the multi-way pattern rules. So if you just use functions that are listed in the main README, you would not encounter that. But that one was work in progress back in 2021. And then there is one performance test that's failing. So it seems to be 2 times slower than expected. And also the build system doesn't work. So you cannot build it from source. So essentially, most of this have to do with building and experimental stuff. So the only thing that affects kind of the publicly available functions is SetReplace git SHA, which you don't really need. I mean, if you just use the latest version, which is version from 2021, you don't really need to have the git SHA. And then I find, at least in some cases, there is a performance degradation. So I'm not sure why that happened. But still, as you can see, most of the things are still working. Yeah, so let me now talk about demo 3. Yeah, so for demo 3, I'm going to talk about expression deduplication. And so this is still not implemented SetReplace, and is kind of an open problem. Yeah, but before we go into that, I just want to point out that in the SetReplace repository, there are a lot of open issues, and you can find some interesting things here. So for instance, if you look at token deduplication, and token, by the way, just another word for expression. So if you look at token deduplication, then there's some description here, and then there's a notebook, which is what I'm going to talk about is based on that. But also, if you're curious about generating the videos of hypergraph evolution, you can find some stuff about it here as well. So anyway, speaking of expression deduplication, so let me explain what the problem is. So in the global multiway system, one advantage you have is that when you get a state, well, because you always dealing with the complete states, once you find a way to, once you find 2 states that are isomorphic to each other, you can just merge them. But in this case, because you are dealing with a single expression events graph, merging expressions is not that simple. And so, but still, we want to be able to merge expressions in some cases, because if we get 2 branches of evolution which produce the same substates, you want to be able to merge them together and have expressions with in degree of larger than 1. And so ideally, we want the original expression events graph to still be recoverable, but we also want to have deduplication be unique. And we ideally want to only deduplicate branch-like expressions, not space-like or time-like. And so one observation is that that doesn't actually seem to be possible. Because, for example, consider this system, and this is an atomic state system, meaning that each expression is just one number rather than a list of atoms. And so here, I mean, so the rule is just an explicit set of rules, but I mean, it doesn't matter what the rule is. It's just a point about the structure of the expression events graph. And so you can see here, we can get, we get 2 branches. And one branch, we get 1, 3, and 2. And another branch, we get 2 right away, and then 4 and 1. And so if you use a different event order, you can have these two, which are subgraphs of this full expression events graph. And if you look at these subgraphs, these are kind of a classic way where you would want to deduplicate the states. Because again, these ones are essentially the same as the global multiway system here, because each state always consists of a single expression. And so it's hard to see how you would deduplicate without merging this 1 and 1 at the ends here and 2 and 2 here. But then if you also want the deduplication to be unique, you don't want to break the symmetry by only deciding to merge one, but not the other one. But if you merge them both, then you get a time loop. Because now you get to 1, which is the same as the other one, and then you can get to 2 and so on. And so it looks like that demanding a unique deduplication automatically creates time loops, or just loops in the expression events graph. So that's interesting, but there's another problem, is that some of the states can be automorphic. So for example, here we have 7, 7, 8. So we have again 2 branches. It branches at this 0 expression here. And then we have 7, 7, 8 on the left side and 7, 7, 8 on the right side. And you can deduplicate them by deduplicating these 2 7s in a different way, because you can either merge the first one and second ones together. You can merge the first one, the second one, the first one. And then you get different expression events graphs. So that again means that you cannot have deduplication to be unique as long as you have the same expressions with the same contents appearing multiple times. So that's one thing you can do, which is you can just merge everything. So every time you have a particular expression, you just merge it no matter what, even if they're space-like or time-like. So that is at least unique and consistent. The problem is that you do lose some of the information. Because, well, once you merge the space-like and time-like expressions, you can use the same algorithms for determining if two expressions are space-like or branch-like separated, for instance, because if there's a single expression, I mean, what does it even mean? Because you can merge a pair of space-like expressions and then also some branch-like expressions to it as well. But what it appears to be is that it's well, there's some more examples here. But basically doing the expression events graphs like this, where you deduplicate all of the equivalent expressions with each other, no matter the separation, is that it's an intermediate stage from the rules to the evolution. Because what you can do is that you can generate this deduplicated expression event graph, which, by the way, is just a pattern net. And then you can use that pattern net to generate the full expression events graph. Yeah, so that's one thing you can do for the duplication. But the problem is that even that doesn't work if you have atoms created on the right-hand side of the rules. Because in that case, all of the atoms you create are just different. And then you cannot deduplicate them based on contents, because that would never deduplicate anything. And so the question I was trying to figure out back in 2021 is how to do deduplication in the hypergraph systems where you'd create new vertices on the right-hand side of the rules. And I think this is important to understand if you want to do any kind of large-scale enumeration of the rules, because essentially we need to know how to run them. And we can run a single-way evolution, but then we need to know what's the event order that we want to use, which is arbitrary. I mean, we can try to run the global multi-way system evolution, but then it's too slow, so we cannot get very far. And we can run the multi-way evolution without any duplication, which works, but then again, we don't have any kind of interaction between branches. And so, but it looks like, at least in some cases, there should be possible to gain some optimization by duplicating them. And then also, of course, the other question that's physics related is, if we do the duplication, what kind of interference between different branches we can get? And can we get it to be anything similar to how quantum mechanics works? Because, of course, normally, I mean, you can get probabilities, but you would not get complex amplitudes from those kind of systems. So the question is, if you consider some kind of interaction between branches, can you get complex amplitudes in a more natural way than just putting them in there by hand? And so, yeah, so this is an open question. Okay, so that's pretty much the end of my talk. And I think we can spend the rest of the time for questions.
Thanks, Max. That was great. Just wanted to find out if we could get the location of the code for the animation that you mentioned wasn't merged.
Yes, so there is the issue called evolution video, and there is one notebook attached to it So, I mean, that explains how to do it. So basically well, it's a spin electrical system. And so the way you do it is that you do a live spin electrical simulation by having an electrical force between every pair of vertices and then spin force between every vertex connected by an edge. And then when you do the rewrite, you just remove some of the vertices and then put new vertices if the rule creates them in the vicinity of the vertices that you removed. Yeah, and so there is a code here that presumably generates the video. I mean, I didn't look at it for a while, so I'm not sure if it will still be working, but at least you can see how it's supposed to work.
Okay, great. I'll find it there. Actually, I had another question as well. In terms of optimizations, were there any specific methodologies that you used, memoization, caching, e-graphs, anything like that that was interesting on just the optimization challenge?
Well, so the main thing is how SetReplace runs evolution to begin with. So it's optimized for the case where you have connected left-hand side of the rules. I think I have it written somewhere. Yeah, so you have simple patterns, meaning that it's hypercast substitution system, not a general pattern rule. And then you have vertex degrees in the states that are all small. And the left-hand side of the rules are connected and small. And if all of those are true, what you can do is that you can keep an index of all matches of the left-hand side of the rules that are possible at any given time during the evolution.
I see. That's smart.
And then when you need to apply a rule, you just find, and you can keep them also sorted at all times. And then when you need to do the rule, you just pick the first one, which is of log n basically, and then you apply it, and then you delete all the matches for the expressions you just deleted. I mean, assuming you're doing single way evolution, and then you only need to create matches for the output of that single event. And so, assuming the rules are small and the vertex degrees are small, one event can run in off side of the rule, essentially, regardless of how large the state is. And then you can run the entire system in linear time. But of course, when you run into problems is when the number of matches doesn't grow linearly with the state. And so one case of that, when the left-hand side of the rules are disconnected, because of course then you get, with two connected components, you get quadratic number of matches right away. And also if your degrees are large, then you can have an exploding number of matches for similar reasons, because you can start to have combinatorial number of matches.
Yeah, for sure. Have you got any intuitions maybe about how to handle those cases as well? I haven't thought about it.
So with disconnected left-hand side of the rules, we just need to we need to handle them separately, because if the left-hand side of the rules are disconnected, they're just a pair of separate matches. And so that's pretty simple to handle. It's just not implemented anywhere right now. But all we need to do is just first split the left-hand side of the rule into connected components, and then keep in our match index, we just keep matches for all the components separately. And then we select matches for all the components separately. and then internally, combine them when we actually make the event. So that's certainly doable. So with vertex degrees, if they're large, I mean, if we just get combinatorial number of matches and we cannot, there's no way to simplify that, then just the approach that's used in SetReplace just breaks down. But I mean, of course, you can try to do something between. Like if you see the number of matches starts to explode in some part, you can then start to
The quad tree or
you can stop keeping the matches for that part and produce them on demand. But of course that gets a lot more complicated.
Yeah, makes sense.
I have a question, Max. When you update the matches, do you construct like some kind of partial match so that you can update it efficiently instead of like each time to find the match in the whole list?
So,
right?
well, we don't really find them. So they already sorted according to the event ordering functions.
I mean,
So
like
when
the
you
new match, when like some rule, when you apply the rule, the possibility of a new match appearing, right? How do you find this new match? How efficient that is to just update a list of matches?
Yeah, so for that, all it needs to do is to search the neighborhood of the vertices in the output of that event. Because if the left-hand side of the rule is connected, and let's say it has a diameter of 2, then we only need to search the output state within the diameter of 2 from the output of the rule.
What
I
if
mean,
there's
that's much faster than scanning the entire. Say again?
Yeah, but what if some like disconnection happens and there's no more neighborhood or something like?
But that's fine because you just do it for every output expression, every output hyperedge.
But what if the rule itself like disconnected, the left-hand side of the rule? Yeah, I know we haven't considered those, but in principle.
Well, if the left-hand side of the rule is disconnected, you just have to deal with matches for every component separately.
Yeah, that's clear.
But other than that, so suppose you split the left-hand side of the rule into connected components, and then you can create a separate match index for each of those connected components. So you can still find the matches quickly, and then once you get the output, you again, match it to every connected component of the left-hand side of the rule.
I see. So basically,
Yeah,
it's always some constant, right? Or big O of constant to find the new match after you rewrite the hypergraph, right?
Yeah, so I mean, it's a function of the exponential in the size of the rule, but not in the size of the state. So that's the important part. It doesn't scale with as the states go larger unless the vertex degrees are large.
Yeah. Well, rules are usually pretty small anyway, so.
Yeah, so that's what it's optimized for.
Yeah, makes sense. Thanks.
And you can say, I mean, I ran it for 1,000 events here, but you can run a lot more, like 10,000, 20,000. 20,000 should still work. Yeah. It actually, the bottleneck is in the hypergraph plot if you want to plot them. So you can get the evolution for 100,000 events fairly quickly, but you cannot really use hypergraph plots to plot it.
Yeah.
Very cool. I had a follow-up question on the kind of open problem that you left us with on the quantum side of things. You mentioned that getting the complex amplitudes is the challenge now. Is there a way you can maybe just a little bit elaborate on that, and maybe have you thought about some ways of getting the complex amplitudes, perhaps?
Well, the question is, how do you compute probabilities that you would get a particular expression in the output? So if you just generate a bunch of random evolutions, and then you compute probability by the fraction of evolution that contains that hyperedge, you are not going to get any kind of complex amplitudes. So it's just classical probabilities. So to get complex amplitudes, you need some kind of interference between different branches, and without the duplication, you just would never have it. But the duplication, I think it's important to kind of understand that quantum mechanics also needs, like just ordinary quantum mechanics needs state deduplication to work. Because if you don't have state deduplication, then in your path integral, all the branches are just separate, and they all have the same probability.
How does deduplication helps to have destructive interference though?
It's destruction of which way path information, isn't it? The same thing?
No. I mean, it's clear when you merge your paths just gonna constructively interfere. You just somehow sum all the paths to your merged state. But how does destructive interference emerges?
Well, that's the question. But I mean, whether it's constructive or destructive, you still want it to have complex amplitudes.
Well, it don't have to be complex. It's at least negative. If you can show that the negative probabilities, it's enough. You don't have to have complex. So you just need to explain where the destructive interference come from, so that you can subtract the number of paths from one branch from another, something like that.
Well, I mean, yeah, fair enough. That's my point. But yeah, you cannot do it for sure without expression deduplication, because on the local level, you need to understand where two states are the same before you can even do a path integral. Because in the path integral, you get to the same state, via multiple paths, and then you integrate all those paths. But to get to the same path, to get to the same state with multiple paths, you need to have state duplication, and you need to have it on a local level, because you're not, well, because you're trying to think about the part of the system and not the entire universe when you do that. And so I think that the understanding expression of the token deduplication is a prerequisite for that. But even then, it's not clear why we would have any kind of destructive interference to begin with. And I mean, you can put it in by hand, because you can attach some phase which you can emulate with different ways. You can attach a phase that just increments, I mean, basically you can attach a circle to every expression, where every time you apply an event, you move something along the circle, and then when the circles align in some way, you can have another rule that would destroy expression there. So you can kind of manually make destructive interference, but of course it would, like, it would be better if it just came out automatically instead of you had to put it manually. But of course it could be just a specific rule that has destructive interference, and it's not a feature of the system at all. That's a feature of a specific rule. So I mean, that's definitely possible.
Well, I was also thinking about, because you mentioned that the loops are kind of time-like loops are kind of bad, but I think like those loops are maybe also the key, because when they're allowed to go back in the state, because you have reversible evolution, you can have two types of events that go forward and go backwards, and those can be thought of like some positive and negative. And basically, if you somehow interpret your probabilities as aggregation of those, so that you subtract number of counts of positive minus negative, then you can have destructive interference emerging from that without putting it by hand. Like something along those lines.
So can you say it again?
When you have loops, right? When you allow to
Yeah.
reverse your states backwards, right? You're in a way producing events that are like updating in two directions in time, even though it's a one computational time as soon as you unroll the single way causal graph, but you still have some kind of total ordering on of your multi-way system, so you can assign some kind of time ordering to your events. And when you assume that your actual probability is interpreted as a like basically the difference of positive minus negative, you can have destructive interference if you just count those, like count your events like this.
Like edge multiplicity or something.
No, not necessarily much. I don't know exactly how that would work. I imagine, like, yes, if you unroll your causal graph in the time loop and you have events that produce some state in the positive direction, you just count those events, and you count the same events that uncompute the same state, and you have some bias of forward time direction events over negative direction events, so that there are more forward ones, so you can normalize it to 1. That can act as quasi-probabilities from quantum mechanics, and you can recover the probabilities from that.
Well, I mean, I still don't see why it would be destructive, because I mean, a destructive interference, you still get to the state. You just get
have to
to the state in a different amount of time, and that gives you either constructive or destructive interference.
Well, you have to interpret that's what I said. You have to interpret what it means to have a observable probability. It's not how probable this current state is, because this state is basically you encounter it in the causal graph multiple times because you have some time loops. You kind of can compute the state and compute it multiple times, so that you can basically have to count how many times you encounter that in forward and backwards direction. And as soon as there's a difference, and so that you can normalize it to
What I
1.
mean by backwards direction, there's no backwards direction necessarily. You just can get to the same.
Yeah,
I mean, like,
there's
look
still,
at this
there's still
example.
computational time. It's still a computational forward direction, but you can still foliate the multi-way system so that you can kind of assign a directionality, so that you can prescribe some total ordering. Of course, if you unroll the causal graph, it's just forward, and there's no time loops, right? It's always going to be a cyclic, but in a way, you can still, as soon as you have some total ordering, you can prescribe this directionality to events.
Well, sure. I mean, that's one of the ordering here. You can see some of the edges go up. But it is kind of arbitrary.
It is arbitrary. I'm not saying there's a unique way of doing it. I think it's like also depends on how you totally order all the states in the multi-way system that has loops in it. You merged all the states. It's like your multi-way system is no longer cyclic. It has some loops in it, but there's still some bias because you somehow total ordered all the slices of the multi-way system, and you can prescribe when you move from one slice to another. And that's how you basically can assign this sign positive or negative to each event. Yeah. And then you can recover these quasi-probabilistic properties and destructive interference.
And I'm still not sure why there would be destructive interference.
And depends on where you place the observer. So if the observer is sort of covering parts of it that have not, that are,
Well,
have,
it's observer dependent, right? It's like you have to imagine there's an observer that not just encounters this state and how frequent it is, what's like the time residency of this random walk on the multi-way system in that particular state. It's actually somehow observer aggregates all the events coming into and out of that state. So that for some reason the actual event of measurement, the observed probability, is proportional to the difference of those events. This is like, of course, this is hand-wavy argument, but
So observer is another set of expressions somewhere to the side of this.
yeah. In the causal graph, it's just you can, for example, imagine an observer is just another chain of time-like separated events. And there's a system that observer cares about is just projections of that another chain on that chain, right? But so it observes some number of events, and as I just described, there are two types of those events. You have to kind of with this hand-wavy argument explain the destructive interference that there somehow observer only allowed to observe something proportional to this difference of those events. Somehow, like because you have a positive event and negative event, is basically cancel each other out. So you only observe the bias of how much more positive the events than negative are there. So the actual probability that observer would measure is proportional to that.
Right. So I think I start to understand what you're saying. That again seems like it would be a feature of the rule. And I mean, what I was talking about is attaching circles to different places in the state and then moving them at every event. It's kind of similar to that because you can just have one of the rules that would do something if the circles are, say, at the opposite phase.
Yeah, you can build it in, but I think it's you can even prescribe this sign instead of assigning it to some events. You actually have this explicit sign in the state, and you have a rule that subtracts two different tokens that have positive and negative sign, but the same token, right? Somehow annihilates them or something like that. That's how you can have destructive. But it's like there's still, of course, if you put it by hand, it's not fair game anymore. And probably there's going to be
it could be fair. I mean, because at the end of the day, you just need to find one rule that has, the general relativity and quantum mechanics in it. So if you just find one rule that has destructive interference, I mean, that's already good enough. I mean, of course, it would be more natural to expect it to be a feature of the, the whole system itself, but it might just not be the case.
Yeah, well, the problem with this rule that has explicit destructive interference built in is like exactly the same problem as Bell inequalities have, so that you can those would have to essentially act non-locally in order to explain the violation of Bell inequalities and like that. So I actually have I don't know. As soon as you have a rule explicitly acting on states and performing this destructive interference.
Well, we can have a rule acting non-locally.
Yeah, we can. That's kind of crazy. So it depends.
Well, I mean, there could be long-range connections in the state.
Yeah, we can have like a hypergraph have some hidden connection always. Like an entangled pair can be thought as just just a single edge extended between these like very far away parts of the hypergraph that can still be somehow rewritten to have this non-local effect. But that's basically equivalent to having non-local interactions built in by hand, which maybe I don't know, not very attractive to me.
Yeah.
Is Shadra still here? Maybe Shadra had some questions because her project is a little bit related. But otherwise, Max, or we can, if I do like some pull requests on the repo, which is like pretty cool. I didn't realize there was that much documentation. Would you be able to look at it at some point? Like, can we contribute?
Yeah, definitely. Well, Yeah, I was going to work on it after 2021, but I guess it's really hard for me to combine, full-time job with doing other research. But yeah, I definitely should get back to it. I mean, I at least should restore SetReplace so that you can build it and at least CI works and stuff like this. But yeah, the main obstacles to doing a pull request right now would be that CI is not working and some of the tests are failing. So you cannot really build it.
The CI code is there, right? So we can just fix the CI as well.
Yeah, of course. So the main issue is fixing CI, that we need Wolfram language running in there. And so the CI it uses here is Circle CI. And so there used to be a Wolfram language image, Docker image there, which was an internal one. So I mean, I can't use it anymore.
Oh, okay.
But I mean, I'm sure we can figure something out because I mean, I know there's a way to use credits to because it's also all CI instances are all ephemeral, so you need to create one and then run something and then destroy one. So, but with Wolfram script and cloud credits, it's possible.
I love this intersection of physics and software engineering. It's so interesting. Cool.
Yeah,
Okay,
but
that's
we
all the
need
questions.
software engineering because with cryptography writing, you really need a lot of tests because if it's not running correctly, you just wouldn't know. And then all your research is wrong. So I think tests are pretty important.
All right. Are there more questions for Max? If not, then let's thank.
By the way, if any of you want to try to do some, I guess, archaeology and fix SetReplace, with at least next weekend, I mean, we can definitely do that.
Definitely.
Oh,
Max
I mean,
is
if you
available
have
on
any other
Discord,
questions,
right?
you can. I mean, I'll be around for this weekend at least.
And if you can drop some of the material on the Discord in the physics channel, Max, people can then have a look at some of the demos or notebooks.
Yeah, for sure.
All right, let's thank Max for this lovely talk. And please continue the discussion with him on Discord. There are lots of people here with great interest in programming. So thanks, Max. Thanks, everyone, for being here. Let's get back to project work. Thank you. Bye-bye.
Thanks. Bye.
Thank you.
Bye.